So the gas variables that we've been studying, I've been asking you to understand them, how they affect gases intuitively, meaning how would the space that a gas exists change if I change the pressure? For instance, if I have a liter of a gas, it's the space it takes up, and I have a certain weight pushing down. And if you notice, I have a manometer attached to this closed tube, so it's like a barometer. And if I was to add twice as much weight, force pushing down, obviously I'm going to compress this gas into a smaller space. And you can see that I made half the volume that I had here. So if I make the volume half by increasing the weight on top, the pressure inside here is going to actually double. And you can intuitively understand that. Look, we go from 720 here, we're supporting 760, millimeters of mercury here, and 1520 millimeters of mercury here. We doubled the pressure because we halved the volume. And intuitively it makes sense because molecules are flying around and bouncing around, and if you make them exist in a smaller space, they're going to bounce around and they're going to hit the container walls more often and create a force that's greater. In this case, that force is going to push down on this liquid greater as you make this space smaller. That's intuitive. Now that's called Boyle's law, and you don't have to know the name, but it's an important relationship. And it's that pressure and volume are inversely related. Now, what does that mean mathematically? Because we have to take our intuitive understanding and make it mathematical. Well, in an inverse relationship, we would say that volume is equal to 1 over pressure. Okay, times, believe it or not, a constant. Now, this constant represents when temperature and moles. So this K really represents the number of moles, as we talked about as N, and also represents that constant temperature. So it factors in those variables that are staying constant, okay? If in fact this gas is acting as a perfect ideal gas, which we'll talk more about. Now, what we're going to do here is that, well, V equals 1 over P. How is that an inverse relationship? Well, think with me for a second. We did what with the volume? We decreased the volume from these two pictures. So if the volume decreases and it has to equal this 1 over P, mathematically you should understand if I lower this volume, this expression, whole expression, only gets smaller if the denominator gets bigger. Now, if you don't see that mathematically, watch. If I have, let's say, the number 10, okay, and it wants to equal 10 over here, then I would have what? 100 over 10, because 100 divided by 10 is 10. Now, if this number gets smaller, that would have to mean that the number on the denominator has to get bigger. All right? Case in point, to make things simpler, if this number goes down to, let's say, 1, okay, so let's make this go down to equal 1, how can 100 over 10 go to 1? You would have to go to what? 100, okay, over 100. So what I'm saying to you is that for this expression to get smaller, this number has to get bigger. And you can check my math, 100 over 100. We went from what? A 10 to 100. So you think with me for a second. The volume went down 10 times, and the pressure, that's the denominator here, increased 10 times. 10 times 10 is 100. Notice 100 over 100 is 1, and this is a 1. You should all know that anytime you increase the size of your denominator, 1 over 1 is 1, but 1 over 2 is what? 0.5. As this number gets bigger, its equivalent gets smaller. Like 1/4 is equal to 0.25. 1 over 8 is equal to a smaller number. So as the denominator gets bigger. So all I'm trying to say to you here is that inverse relationships work that way. Now we can do the opposite. If we were to start here with a what? Smaller volume, and the volume was to increase, then the pressure for this to increase, this whole expression here has to increase as well. But to make a whole number increase, our denominator has to get smaller. So that's why the pressure would decrease. So as we go from a volume, as it gets smaller, if we were to go this way, the pressure decreases. And that's essentially what an inverse relationship works from. Now, let's go back to what we have here. If volume equals 1 over P, and let's just clean this up, all right, because you're responsible for understanding this. So if volume equals 1 over P times this constant, which reflects the things that have to stay constant for this to work. We've talked about this, temperature in moles. I can move this P up here algebraically. I can times this side by P over 1 and times this side by P over 1. And now what do I have? Well, the P's cancel, and I'm left with, well, pressure times volume equals a constant. I know that constant thing is bothering some people, but it has to equal some number. Because if you think with me for a second, and I'm always asking you to think with me, if pressure increases, volume will only decrease if we're always equal to the same number. Now let me show you what this means. Let's pretend this K is equal to 20. Okay, let's scroll down. And let's just pretend it's a constant, right? Temperature and pressure, temperature and moles are staying constant, so these numbers are always the same. All right, so you should just fill these in with me, but very simply, 1 times 20 is 20. Let's put some factors here. 2 times 10 is 20. 4 times 5 is 20. 5 times 4 is 20. And then 10 times 2, and then 20 times 1. I just made all the factors. You've done this in math, I'm sure. Now, if you notice, these things always equal the number. Now, why do they have to equal 20? Well, think with me for a second. If, again, I'm always asking you to think with me, if the pressure doubles, all right, the volume halves. Look at that. If the pressure quadruples, goes up 4 times, the volume goes from 20 to 5. What does that mean? That means the volume goes down to a quarter of its original. Let's look at this again. If the pressure goes up 4 times, the volume goes down to a quarter. You can see that 4 times 1 over 4 is always equal to 1 if you want to make the K 1. Look what I said here in the following example. If the volume is halved, right? So let's go clean this up. Let's go find another number. Let's go with magenta. The volume is halved. So we went from what? This to 10. The pressure does what? It goes from 1 to 2. It doubles. And that's how an inverse relationship works. Let's graph this. Okay? Let's graph this. And I'll show you what the curve is supposed to look like. Now, I didn't show you this last week, but now we're getting into this. So let's plot this. Let's make this a 1 for a pressure. And we have 20. So let's make the point right here. Then we have 2 and 10. I'm just plotting this. The pressure is on 2. So we have 2 for the pressure. And now we're 10. Now, this was 20. So 10 is somewhere in between. So my point is right here. Then I have a 4 to a 5. So the pressure goes to 4. I'm just plotting these changes. 4 and of course 5 is somewhere in between. Then I have a 5 and a 4. So this wouldn't go too much. Then it would go, if you're looking down, a 10 to a 2. 6, 7, 8, 9, 10, and a 2, and then a 20 and a 1 somewhere over here. Okay, so certainly the scale is not terrific, but you can see that my curve looks something like that. And we would say that these lines are asymptotic, meaning these arrows approach the X and Y axis, but they never get there. And it's very important, okay, why they do not. And we'll talk about that in one of our labs. Okay, but let's get started. So yeah, this is the curve. So the pressure volume, the Boyles law pressure volume curve looks something like this. And it's because as one goes up, the other one goes down, okay, the inverse of the change. So if something increases 3 times, the other one goes down to a third. Okay, if something increases 4 times, the other one goes down to a fourth. Okay, that's an inverse. And why does that work? Because volume is equal to 1 over P. Watch. If the volume increases 4 times, then this has to do what? Has to what? Decrease 4 times. Okay, so that's how that all works. Or it goes down to a quarter. All right, so any case, moving forward, let's look at this mathematically. Okay, look at our first question. Now we're going to start doing some math here. Now, some questions you can do and understand without the math, but the intuitive nature of what we're doing really helps. So let's look at number 1. A volume of a certain obscene gas is 40 milliliters, and the pressure is decreased from 4.3 atmospheres to 1.2. What's the new volume of the gas at constant temperature? All right, well, we're going to go to something called Table T to look at our only gas law. But what I'll say to you is this. We know that volume and pressure are inversely related. They equal to a K. Now, what is that K? The other things that are constant. But we also know that temperature is also related to volume and temperature, to volume. Now, I'm going to put the T here, and you say, why am I putting the T there, the temperature? Well, I'm doing that because I know that volume and pressure, they came from this relationship. Volume was equal to 1 over P times a constant. That's an inverse relationship. Volume is equal to temperature, and of course Kelvin temperature, all right, times a constant. So these guys are equal. So if I bring the P, all right, like we did algebraically, to the top, and I want to what? So the P is really here, and I want to bring the T over, okay, we know algebraically it would go to the bottom. So because of those relationships, and what are those relationships? Well, those relationships are a direct proportion. Something equals each other, one doubles, the other one doubles, and here is a indirect, one goes up, the other one goes down. When you put them all on one side, what you get is something called the combined gas law. Now, as I said, the K equals the other things that are staying constant, or the other variables. So if V times P over T equals K, then doesn't K equal VP over T? Yeah, these equal each other. So if you didn't quite follow, this expression leads to volume pressure over temperature equals volume pressure over temperature. And this I always call the current scenario, and I call this the future. So if we have a volume, pressure, temperature variables for a gas, and they become new, which means we change the variables, then we can solve for any one of these new ones. Okay, so let's go to Table T and let me show you what I'm talking about. So in our reference tables, we would go to the Table T, where a lot of our formulas are, and we would see where we've used temperature conversions, we've had our heat, we haven't done anything here, but if you look very closely, we're going to deal with the combined gas law. And look how they write these guys. They have P1, V1, T1. These are the current conditions and variables, okay, of one gas, and these are the new conditions, or I say the future. All right, so we're going to be dealing exclusively with this formula. So I like to call it vice presidents over teachers equals vice presidents over teachers, but again, it's given to you. So whether you write PV over T or VP, as written in the reference table, it does not matter. But what I want you to understand is where they come from mathematically. We're solving for two things: indirect proportion, bringing the p up to the top, that's why it's next to the v, and of course, bringing the t down because v equals t directly proportionally. Okay, so let's do this math problem with our newly discovered and acquired um, ideal gas law formula. And there's a way to do this. You have to be able to do this problem this way. So let's write our formula down. I like to do Vp over T, that's the current scenario, and I do Vp over T, the future, or the future. Okay, so if the volume of an obscene gas is 480 milliliters, all right, so this is my current, right? This is my current condition. You have to be able to put the variables together. This is the current. So I've got 480 milliliters. I'm writing out my units. I'm not being lazy. Okay, there's my volume. And the pressure is decreased from 4.3. Now this 4.3 goes with the 480 because you have a current gas at 480 with a current pressure of 4.3. And notice the unit's atmospheres. It's one of our units that we've been working with. Okay, and they're saying it's decreased to 1.2. That's a new scenario. That's a new condition. So that goes over here. All right, so I put 1.2. That would go in the place of the pressure, atmosphere. Okay, what is the new volume? That'd be over here. They're solving for V. You can make that X if you like, but it might as well leave it V. Notice they say at constant temperature. Now, if it's at constant temperature, well, we don't need this. So we just cross out the variable that we don't need. So the equation becomes Vp equals Vp. No need to memorize new formulas. Just cross out the variable that stays constant. Now we know temperature is staying constant, and so is moles. They're not going to say that, but we know better. Okay, I need you to be able to do two things here. Come up with the answer and also rearrange it properly. I'm asking you to rearrange it always this way. So we're going to solve for V, and I want you to do this. I want you to bring the 1.2 down. Now why? Algebraically, as we talked about before, we're going to times this side by 1 over 1.2, and we'll times this side by 1 over 1.2. Why am I doing that? Because I want V by itself. We're just doing algebra. Or if you remember that little shortcut, bring the 1.2 to the bottom. So I'm rewriting this, 480 milliliters times 4.3 atmospheres, and then all over now 1.2 ATM. All right. Now I'm going to cancel. Well, before I do that, I'm sorry, and I could cancel and be my merry way, but because there's plenty of questions you will see where they just want the setup, watch what I do now. I want you to rewrite it this way. Where it says setup, here's what I want you to do. Put the like unit over like unit. In this case, it's 4.3 atmospheres over 1.2 atmospheres. And who's left standing? Times 480 milliliters. Now you may say, well, isn't that over 1? Sure, but you don't have to write that. And that's the setup. And the reason why I want you to do that every time is because this right here is an answer. You'll see answers where they just want the setup. And sometimes people have a tough time moving from this initial setup to this point here. And what you do is you just algebraically solve for your unknown, okay, doing your algebra, and then you put like units over like units, like 4.3 over 1.2 times 480. And of course, you know you did it right if the units that you don't want cancel, and you're left with milliliters, which is a volume unit. So let's go find this number. So we're going to take 4.3 divided by 1.2, and we times it by 480. And what you should get is 1720. And that's milliliters. And that's your answer. Now, of course, if we're using our sig figs, this says 2, this is 2, so our answer should have 2. So this answer should be 1,700 milliliters. Now, I'm asking you to do one more thing. Does this number make sense? Does this number make sense? Think with me for a second. We have 480 milliliters. We're saying that's going to jump to 1,700 milliliters. Wow, that's a huge leap. Now, if you think with me, let's see, 4 times 3 is 12, 4 times 4 is 16. So it's about, okay, it's about a 4 times increase in volume. So what should the pressure do if it's inverse? Well, because we know our relationship, pressure should decrease to about a quarter. So what's about? Now we're making estimates here to make sense. What's a quarter of 4.3? You can just test this out. 4.3, okay, divided by 4 comes out to be about, I don't know, 1.075. So what I'm saying is that the pressure, it wasn't perfect, but these are estimates, definitely went down to about a quarter. Okay? So what we're saying here is that you can make some estimations. Does this make sense? Absolutely. If the pressure is going down to about 1/4, then the volume should about quadruple or increase 4 times. And that's what our answer reflects. Don't just be a robot and come up with a number. See if the number makes sense, and it does in this case. Okay? So what I'd like you to do is try number 2. And I would like you to solve for it, plug in the values. I want this setup. I want to see it just like this, and I want to see your answer. Okay, try that right now. Stop the video. I'm going to do it, and when you click it on, you're going to see my answer. So stop me now, please. Okay, I'm back, and you can see the answer is 52 kilopascals, but I'm asking you to do what? I'm asking you to go from plugging in to rearranging and then eventually solving. These are skills you must have, because again, this problem could be given to you in a scenario where you just need the setup. And if you just cross multiply your hearts away and don't use your units and don't do this, you will not get it right. But let's go back in this question. If a pressure of acute gas is 160 kilopascals, that's the current pressure, changes from 5.2, that's another current condition. Remember, current, future. What is the new pressure of the gas? Now, they didn't give us a temperature, so you cross it out. You have to assume that temperature is constant, and what also is constant? Of course, moles. So that's why there was no temperature involved. So I solve for P. This 16 went to the bottom algebraically. I put like units over like units, 160 over 1 if you have to, and then that this could be how a multiple choice question, hint, 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 could be given to you. All right, and this number. Now we're still not done. Does this number make sense? Let's look at our relationship. What happened here, party people? We went from 5.2 liters to 16. That looks like we increased 3 times, about 3 times. Okay, and so if my volume increases 3 times, then what should my pressure do? Decrease to about a what? Third, because of our inverse relationship. So 160 should be about a third of its original position, and 52 is about a third of 160. This number makes sense. The math has to follow the concept. This is brand new to you guys. It's just not a math problem. It's a math problem that reflects understanding of why it works. And unfortunately, you don't get that in mathematics too often. So that's where we're going to finish with this. I want you to go to the other worksheet I gave you. Okay, so we've been focusing on Boyle's law okay, relationship in this um, lecture. So we're going to do some of these that are mixed. So what I want you to do is I would like you to do the following. Number 9, number 10, 11, 12, 13, and 14. Some of these are going to require the formula, and 15 and 16. So essentially 9 through 16. And some of these are not going to require any math because you're going to intuitively answer them based on your understanding of Boyle's law. I'm also going to throw in a question, all right, from last week's understanding. So if I'm going to throw in number 4, and I'm going to throw in number 5. Now, these aren't Boyle's law, but these are intuitive things. You don't need any math here. Just intuitively answer those as well. Make sure you review your work with your keys. See you later.